Okay, in this problem we have to find out what is the mass and position of this ball right here. So to do this, we really have to find out what is the balance of torques on the top part first. So if we look at this clearly, our pivot point is going to be right here. And so my total clockwise torque here is going to be held by the ruler itself is going to go this way, and of course the 6 kilogram mass is going to go this way. And then the counterclockwise torque would be on this string here, which would be going that way. So first for the ruler itself, if it's a 60 centimeter ruler, then or stick or whatever pipe, if it's 60 centimeters, then the midpoint would be at 30. And if we're 20 away from the left side, we've got the 5 here and the 15 here, the total of 20 over, the midpoint would be at 30, so that would be a total of 10 over. So the 1 kilogram would be hanging down here. So 1 kilogram is hanging down here where that's 10. So we have 1 kilogram hanging 10 away from the pivot, and then we have that 6 kilogram one that is hanging 20 centimeters away from the pivot, and that's our total clockwise torque. Now our total counterclockwise torque is just going to be 15 centimeters away from I don't know. So we just put those two equal to each other. Excuse me. And we find out, of course, 6 times 20 is, wow, sorry, my body's acting up today. So 6 times 20 is going to be 120, and then we're going to add 10, so that's going to be 130, and then we're going to have 130, and we're going to divide that by the 15, and that's going to give us 8.66666. So the total going down this one must be 8.666 kilograms. That makes sense? I hope. Okay, so then we have to look at the bottom one. Now we have a balance of torques on the bottom one. And the balance of torques on the bottom one, again, my pivot point is going to be right here, and we do this in a different color. So if my balance of torques is here, then this 2 kilogram mass is clearly going counterclockwise, and everything else is going clockwise. And we have a 0.3 kilogram stick. Well, if the total of the stick is 45 centimeters, then 45 divided by 2 gives me 22.5. So 22.5 is the midpoint here. So if that is a total of 15 over here, then 22.5 is going to just be 7.5 for the stick. So I'm going to have 7.5 centimeters, and the stick was a 0.3 kilogram mass. That's going this way. And my unknown is going to have to go somewhere. And then my counterclockwise one is, of course, 2 kilograms, and that was a total of 5. So 2 times 5, of course, is 10, and that's going to equal 7.5 times 0.3, which gives me 2.25 plus x. Now, first I got to figure out, well, I can figure out what the overall x is here. Obviously, it's going to be 10 minus 2.25. So if I have 10 minus 2.25, that's going to give me 7.75. So 7.75 is going to equal the force times the distance of the ball that's hanging over here. I don't know what the distance is until I find out what the force is. Of course, we're using mass instead of force here. That's okay. We've been using it consistently throughout the thing. But up here, we figured out that the total pulling down on this string was 8.666, and I know that this is 2 and that this is 0.3, and so this has to account for all the extra mass. So if we have the 8.666 minus the 0.3 and minus the 2, of course we're going to have 6, and we're going to have 6, and we're going to have 0.3, and 8 minus 2 is 6. So we're going to have 6.366 kilograms must be how big the ball is. So that part was easy. And now if 6.366 kilograms has to be, that's this part, so we have 6.366 times D has to equal the 7.75. So if I take the 7.75 divided by the 6.366, that tells me that this thing has to be way the heck over here, so that this distance from the pivot point to there is only 1.22 centimeters over. And at that point, we would be in equilibrium. So that's all there was for that one.